All right, folks, let's get back at it here in section 10.4, example problems. We've got 10 problems to do, and we are on number 7. So this problem illustrates examples that you'll see in web-assigned questions 14 through 17, and we're going to be using double and half angle formulas for these problems. And I'll refer back to kind of our reference page here. Double angle formulas are these we see at the top of the page. You have to remember cosine and sine. Tangent will be given for you. And then the half angle formula is down here. Remember, there's both a positive and negative version, and you have to determine which of those you need based on which quadrant the angle theta over 2 is in. So let's start by taking a look at this. If we have theta is between 3 pi over 2 and pi over 2, that means that this theta is in quadrant 4. Let's take a look at where theta over 2 is. So I'm going to take everything in this inequality and divide by 2. That's going to give me 3 pi over 4 is less than theta over 2, half of theta, which is less than half of 2 pi, which is pi. So that puts theta over 2 in quadrant 2. Okay, and what does that do for us? Well, we know that the cosine in quadrant 2 is negative and the sine of quadrant 2 is positive. Okay, so let's start by analyzing the geometry of theta and seeing if we can figure out all the different components, horizontal, vertical, and radius that go into this angle theta. So we know theta is in quadrant 4, so I'm going to go ahead and sketch an angle in quadrant 4. Here's my initial side and my terminal side. It's in the 4th quadrant there. And we'll go ahead and make sure we label this as theta. And let's take a look at sine theta. Well, sine of theta is negative 2 over 3, and I remember that sine is equal to the y-coordinate divided by the radius. So that means the radius of this circle is 3 units. And this vertical leg here is going to be 2 units. So what we need to do is determine the horizontal leg. The horizontal leg will be the square root of 3 squared minus 2 squared, or the square root of 9 minus 4. That's the square root of 5. So the coordinates of this point right here on the circle has an x-coordinate of root 5 and a y-coordinate of negative 2. Why is it negative? Because it's below the x-axis. Okay, so we're going to now, we have all the information we need. We have a radius of 3. We have a horizontal component of root 5, a vertical component of negative 2. From those 3 values, we can determine sine, cosine, tangent of the angle theta, and then use that in the double angle and half angle formulas. So I'm going to rip really quickly through each of these formulas. Hopefully you can stay caught up with me. There we have the sine of 2 theta. Now we'll move on to sine of theta over 2. There you have the sine of theta over 2. Notice that I took the positive square root because of the little work we did up here at the beginning of the problem. We showed that theta over 2 is in quadrant 2, so the sine is positive. So this expression right here is considered simplified the way I've written it. There are a number of ways you could have written it. You could have left it like this, you could have left it like this, or you could have written it like this. You'll have to test WebAssign to see which version it will take, but I know that it will take the simplified version there at the end. All right, now we're going to look at the cosine of 2 theta. And the one thing that I want to remind you about is that the double angle formula for cosine, you have 3 options. So we'll go back here and take a look at double angle formula for cosine. You can pick any one of those 3. I'll go ahead and pick the cosine squared minus sine squared version, and we'll grip it and rip it with that. There you have it, folks. That's cosine of 2 theta. It's a nice number there, 1/9. Let's now look at the cosine of theta over 2. And remember that in quadrant 2, the cosine is negative. There you go, folks, cosine of theta over 2. Now we're moving into tangent of 2 theta and tangent of theta over 2. You have a couple options here. You can always remember the identity that tangent is equal to sine over cosine. And we already have the sine and cosine of 2 theta and theta over 2, so we could use that identity to figure out what tangent of 2 theta is and tangent of theta over 2. But I'm going to go ahead and use the double angle and half angle formulas that were given on your reference sheet just so you see examples of those worked out. And we're going to start with the tangent of 2 theta. All right, that's tangent of 2 theta. Notice that I did not rationalize the denominator. If you wanted to, you could multiply by root 5 over root 5 and turn that denominator into a nice rational number. All right, so let's move on. We got one more to do here. We'll have to scroll down to do that. It's going to be tangent of theta over 2. And remember, theta over 2 is in quadrant 2, so that tangent will be negative. And here we go. All right, folks, there you have it. The tangent of theta over 2 is the negative square root of the quantity 3 minus root 5 over the quantity 3 plus root 5. Congrats, you did, let's see, that's 1, 2, that was 6 problems all wrapped up into one. Let's see if we have the time here to go on to example 8. Example 8 will show you how to approach web assigned problems 18 and 19, and in these problems we're going to be using the sum and difference formulas. These are ones you have to remember, so let's go back and take a look at our reference page. Go to page 1 of that reference, down there near the bottom, sum and difference identities for all angles alpha and beta. So cosine and sine are ones you have to remember, tangent you don't need to remember. Let's go ahead and take a look here at the angle alpha. The sine of alpha is 3/5, and alpha is in quadrant 1. So as is always the case, I'm going to encourage you to draw a picture. In fact, let me write it here in nice big text. Draw a picture, because a picture is worth 1,000 words, and the picture will show you all the information you're going to need to answer these trig problems. So alpha is in quadrant 1. I'm going to go ahead and draw an angle here in quadrant 1, sketch in the right triangle, and alpha is this angle here. And our components, well, sine is 3/5, and I know that sine is y coordinate over radius. So that's my that's the picture so far. Now I need to find the horizontal component. Well, that's easy. This looks like a 3, 4, 5 right triangle. So I know that component right there. The horizontal component is 4. Remember, that point has the coordinates 4, 3. 4, 3 is the coordinate of that point that lies on the terminal side of alpha. All right, so that's all good there. Whoa, that is not what I intended to do. Undo that. Trying to move that bad boy. That's alpha. So let me go ahead and label this picture as alpha, and then over here I'm going to do beta. So what do we know about beta? Well, beta has a cosine of 12 divided by 13, and beta lies in quadrant 4 because beta is between 3 pi over 2 and 2 pi. So I'm going to go ahead and sketch beta here. Beta ends up down here in quadrant 4. That's a terrible picture. You deserve better. Let's see if we can get that to look a little better for you. Little better. Okay, so beta is that angle right there. Notice I'm not drawing beta inside the triangle. The triangle just contains the components of horizontal, vertical, and radius that I need to know to calculate all the different trig values for beta. So the cosine is 12 over 13. That gives me a horizontal component of 12. That's going to be our x-coordinate, and a hypotenuse or radius of 13. This vertical component, some of you may remember the famous 5, 12, 13 right triangle. Not as famous as its brother, the 3, 4, 5, yet still pretty useful at times. So now that I have all of those components determined, I'm going to write the x and y coordinates of this point. The horizontal component is positive. The vertical component is negative. So the coordinates there are 12, negative 5. From these 6 numbers, 3, 4, 5, 12, negative 5, and 13, I can determine all of the trig ratios for the angles alpha and beta. And I'm going to need those trig ratios to determine the sine of alpha plus beta and the cosine of alpha minus beta. So I'm going to use my sum difference identities, and this problem's going to be pretty quick once I run through all the calculations. Here we go. There you have it, folks. Sine of alpha plus beta is 16 over 65, and the cosine of alpha minus beta is 33 over 65. One of the things I don't want to lose sight of here is, what is alpha plus beta? Well, it's what would happen if I took this angle alpha and I added beta to it. And what is alpha minus beta? It's if I took this angle alpha and I subtracted beta from it. That seems trivial, but it's really not something we talk much about these. We just kind of figure out how do we do these problems and use the identities to find a final answer. If you want to know more detail about how these formulas, these identities are derived, I'll again point you back to your textbook, which does a nice job of showing the derivations of these trig identities. All right, that's about it for this video. We're going to shut it down, and stay tuned for examples 9 and 10 in the next part.